Okay, we are almost to the link between equilibrium and all these thermodynamic variables we've been talking about. So the last thing we need to discuss is the idea of standard values. So for a given reaction, we can go to a table and look up standard values of enthalpy, entropy, and Gibbs free energy for reaction. So tables of standard values exist. And what is the standard that we use to define these standard values? We write these, first of all, just notation. Delta H, we put a little degree sign next to it. Delta S, and we say it not. So delta H naught, delta S naught, delta G naught. These are the standard enthalpy, entropy, and Gibbs free energy for a reaction. So the standard that we define is that all of our reactants and products are in their standard state at a pressure of 1 bar, which is close to 1 atmosphere. Okay, so what does their standard state mean? It means that if we have to define a temperature, but say at room temperature, what's the regular state of that thing? So if you have, say, hydrogen, then it's going to be in a gaseous form. That's the standard for hydrogen. If you have something that's aqueous, then it's dissolved in solution, and it's at its standard state of 1 molar. Right, and so these are the standard states that were defined earlier when we were talking about things are defined relative to their standard state. Same thing. Pure liquids are in that. Pure liquids, pure solids are in those states. Okay, and so the reason we're reviewing all of this is because equilibrium is related to delta G. Specifically, the relationship that we care about, and what all of this was leading up to, is that the equilibrium constant for reaction K is equal to the exponential of negative delta G naught, so the standard change in Gibbs free energy, divided by R, the ideal gas constant, times T in temperature in Kelvin. So this is for a reaction. Okay, and so this is the important relationship that we've been leading up to. And just again, to reiterate here, R is the gas constant from the ideal gas law, which is 8.3145 joules per mole times Kelvin, although you can write it in a bunch of different units. T, I will just emphasize again, is temperature in Kelvin. So this has to be in units of Kelvin. You can't use degrees Celsius, so definitely not degrees Fahrenheit. And what we can see from this relationship here, mathematically, when delta G naught, because R and T are always going to be positive values, when delta G naught is negative, or when the process is spontaneous, our K will be greater than 1. And if delta G naught is positive, meaning under standard conditions the reaction is not spontaneous, K will be less than 1. So K will, of course, only tell us about systems that are at equilibrium. And in the next video, we'll look at, well, what if something's not at equilibrium? If we just mix something together, how can we determine which way a reaction will go?